the activity of this piece of channel of niobium was 2.6 to 10 to 7 becquerels. And you see that in this cathode deposit, it is 1000 less activity of niobium. That means the separation factor is around 1000. And in anode residue, it is almost all the activity is in anode residue. So that means that it is quite successful separation of zirconium and niobium, and it was just a preliminary results. The further studies undergoing to improve this efficiency. The estimated volumes again without processing is around 10,000 or 14,000 cubic meters, and with processing it is 7 times less. What we can do further with the anode residue, it is niobium, I remind you. So there are several types of the matrices that are proposed. It is either glass, magnesium, potassium phosphate matrix, or murtite ceramic. For electrolyte, it is the most difficult part of the waste. Now we propose some clay materials I will show you later. And for zirconium, it is either zircon itself, metallic zirconium. It is mineral-like type of the matrix called zircon, so silicate. It is cemented of the zircon, because in this case zirconium is intermediate level waste, so we can use cements for this, or also murtite ceramic, because murtite is quite good mineral. It has a very broad range of the cations, and thus in the structure, so it can adopt quite a large variety of different cations in its structure. So the expected economic effect that was estimated 4 years ago, it is from 5 to 15 billion rubles. So quite a good economic effect. About these matrices, these two matrices, so if glass matrix is quite well known, murtite mineral-like matrices like murtite also quite well known, but MPP matrix is also, actually, it is quite old studies of the magnesium potassium phosphate compound started in, I think, in USA maybe 40 years ago, something like that, like this. At least 30 years, I know this works, maybe even earlier. But nowadays, this matrix intensively investigated by my colleagues in Institute of Geochemistry and Analytical Chemistry of Russian Academy of Science. And the idea of this matrix, that again, it is the structure of the main component of the matrix is close to the natural mineral called potassium struvite. So it's like mineral-like matrix, but we can prepare it like a cement. So it is a low temperature procedure. You just mix components, magnesium oxide, this potassium phosphate, maybe depending on the algorithm or methodology, it can be added phosphoric acid or just water. So it depends on the, again, type of the radioactive waste. And then it just cured as a cement material, but it has much higher mechanical strength and the chemical behavior much better. So this type of waste of matrix was tested for the immobilization of both zirconium and niobium, and it was very high stability. So the leaching rate of the zirconium and niobium was less than 10 to minus 6 gram per cubic per square centimeter per day, and it is a very nice results, very good results. Also, we tested it with the radiation test. We radiated it up to 10 to 8 gray, so 100 mega gray. And the mechanical strength, the leaching rate was also the same. Not the same, but they complied with the requirements for this type of matrices for high level waste and intermediate level waste. For electrolyte, for this chloride media, so the problem with the chloride that none of the existing matrices can adopt chloride anion as a structural component. You cannot put chloride in glass because chlorine is volatile, so it will escape this structure. There is almost no stable minerals that can withstand radiation doses where the chlorine atoms would be in the structure. So we proposed another approach. We took clay materials. We mixed it with this chloride melts. Why we choose clay materials? Because clay can adopt in the structure quite a significant amounts of the alkali metals as well. So, and some anions also. So after the mixing of these clays with molten salt, we annealed it at rather low temperatures, less than the temperatures for the glass production. It was around 900 Celsius degrees, and we obtained these compounds, let's say, with 20% of the chloride content, and again tested with the towards a mechanical strength. It was again higher than the limits for the regulatory requirements. It was they were irradiated up to 1000 megagrays already, and they so there were almost no changes in mechanical strength. And the leaching rate was also very, very low for the zirconium and niobium. So these two types of not maybe very new, but quite advanced matrices we used in this case. So, and as a result, you saw that the economic efficiency of this approach for the electrochemical separation of niobium and zirconium is more than 5 billion rubles. So today it's like 15 million US dollars, even more. It was shown experimentally already in lab conditions, but still with the real channel that it is possible to extract more than 90% of the zirconium with the purification factor around 1000. Based on these results, we can say that there is a decrease of the volume of the second class of the radioactive waste more than 10 times. And this approach can be used not only for RBMK reactors that we use, that my colleagues used in the research work, but also for other types of the zirconium structural materials. So that's all for this topic. Thank you for your attention. If you have any questions. Yep, please.
How do you identify the zirconium in sample? and determine zirconium recovery? Because there is no zirconium 93 standard available.
Sorry, one more time.
Now, how do you identify a zirconium 93 and determine zirconium recovery?
Yeah.
Because there is no zirconium 93 in the market.
You mean the calibration, but with the liquid scintillation technique, the same. So
Yeah,
it's a separation.
but to know the recovery, what do you do? How do you do?
So the recovery of zirconium metal, you mean? The piece of channel you saw, it's quite big, so it was easy just to weight it and by mass to analyze it by mass. The activity of the zirconium and niobium was determined by liquid scintillation counting. Yeah.
Yeah, because I use zirconium 95. It's a gamma emitter to know the recovery.
Yeah, here we cannot do it because so we cannot introduce zirconium to the channel, metallic channel, because it was the real sample. So we estimated the recovery by mass. Because it's quite a huge mass and it was easier to determine it.
Okay, thank you.
Anyone else?
Any more questions? If not, then thank you. So I will invite our next lecture.
Is the strontium determinate without cocktail?
Yes.
But
For strontium, it is possible.
yeah, but you need to separate zirconium and yttrium. Oh, excuse me, strontium and yttrium.
Yes, but then you wait 2 weeks, and yttrium is in equilibrium with strontium.
But it's not a 100% the separation.
Yeah, but you don't need 100% separation because when you separate strontium, the half-life of yttrium is 2 days, 2.4 days. So you wait 2 weeks to reach equilibrium. Then you measure the total activity of strontium plus yttrium. So it is a double activity of strontium.
But if you use a cocktail to, I think strontium, it's more affinity, has more affinity with the organic phase.
Yeah.
Then we can do the extraction, and after that, use the cocktail.
Yes, it is also possible. So there are 2 ways. Either you use cocktail or not. If you use cocktail, then you can measure it immediately. Yeah.
Okay, because
also you can really distinguish between strontium and yttrium on the spectrum of liquid scintillation spectrometry, because strontium has much lower energy, so there will be two peaks, and it can be easily they can be easily separated mathematically.
But you use the Cherenkov, okay, to determine without cocktail.
Yeah. But for determination without cocktail, you need to wait for these 2 weeks. Yeah. You can measure it immediately, and after 2 weeks, you will see the increase in the activity due to the accumulation of yttrium 90, and then calculate what was the activity of strontium and yttrium.
Okay, thank you.
Yeah. Okay. Okay, if not, then thank you again, and we will check where our lecturer. Just a moment.
Да?
Мгм.
Можно начинать?
Да.
Hello, everyone. Can you hear me? Yeah, okay. So, I'm very glad to see you here. And I hope you enjoy your summer school, Moscow University, and Moscow itself. So, my name is Alexey Konoplev, and I will give a lecture, Radionuclide Behavior in the Environment of Contaminated Areas, with the examples of Mayak, Chernobyl, and Fukushima. So actually, I graduated chemistry department of Moscow University many years ago. Then I was doing research in hydrometeorological service and environmental monitoring. And then I was invited as a professor to Fukushima University, to newly established Institute of Environmental Radioactivity soon after the accident at Fukushima Daiichi nuclear power plant. So last 12 years, I worked in Japan, in Fukushima University, as a professor and then deputy director of the Institute of Environmental Radioactivity. So now I represent two institutions. First, Laboratory of Geochemistry of Natural Waters at Geography Department of Moscow State University. I will tell you a little bit about that later. And Institute of Environmental Radioactivity at Fukushima University, Japan. So this is a brief information about the Institute of Environmental Radioactivity at Fukushima University. It is located. Есть какая-нибудь? По центру. Ага. Okay, this is Fukushima Daiichi nuclear power plant. And our institute is located in campus of Fukushima University. This is just 60 kilometers away from a nuclear power plant. And therefore, this is excellent location for research on contaminated areas. So here you can see the campus of Fukushima University, two buildings of the Institute of Environmental Radioactivity, and this is the team of the Institute of Environmental Radioactivity. So not very big one, but quite efficient. So this is about my second affiliation, laboratory of geochemistry of natural waters. So last year, we, together with Moscow State University, got the mega grant from Ministry of Education and Science of Russian Federation for, this is a project for 5 years, and project is called Fluxes of Potentially Toxic Elements and Substances in River Basins, Research Methodology, Quantitative Assessment, and Predictions. So the aim of the project is to establish and develop interdisciplinary laboratory of geochemistry of natural waters in Moscow State University. So this is an interdisciplinary laboratory which involves scientists from different departments, not only geography department, but also from chemistry department, from soil science department, and so on. So one of the area of the project is migration in aquatic environment of toxic substances or contaminants. And to develop the principles of emergency response for such technogenic catastrophes, we apply the model contaminated areas which exist already. And today I will tell mostly about these 3 contaminated areas in Eurasia. These are Mayak area and the trace, which is called, let's say, trace of Kishtim accident. But Kishtim town had nothing to do with this accident. This is just closest town. And location where the accident happened was Production Association Mayak, and the accident happened in 1957. However, the radioactive contamination of the environment lasted during the period of 1948, when the Mayak started, till 1987, when the production of weapons-grade plutonium was cancelled at Mayak. Then we will consider the Chernobyl contaminated area after Chernobyl accident in 1986. And finally, we will consider the behavior of radionuclides on contaminated area after the Fukushima Daiichi nuclear power plant accident back in 2011. Okay, let's start with the Production Association Mayak. So Mayak belongs to Russian State Corporation on Atomic Energy, Rosatom, and is located in the northern part of the Chelyabinsk region, near the towns of Kishtim and Kasyl. The enterprise was established at the end of the 1940s to produce and reprocess weapons-grade plutonium. This is detailed map of Mayak location. So you can see here the health protection zone covering an area of approximately 350 square kilometers around the site. Both agricultural practices and permanent residents are forbidden within this zone, although the area is still used for research purposes. A larger area, which is pink here, has also been designated as observation zone, where regular monitoring occurs, but where agricultural practices are permitted. So when we talk about Mayak, we should distinguish different sources of radioactive contamination. First of all, the initial source of radioactive contamination of the environment in Mayak was direct discharge of intermediate and low-level radioactive waste to the Techa River, which occurred in 1949 to 1956. So I understand your school is devoted to radioactive waste management. So this was very bad example, error example of radioactive waste management. So direct discharge to the river. So, however, so at that time, people did know very little about the radioactive contamination of environment, about effect of radiation on population and environment. Moreover, the Soviet Union at that time was in a hurry. You know that in 1940, that was a Cold War area. And in 1945, US dropped 2 atomic bombs to Hiroshima and Nagasaki. So this was a challenge for Soviet Union, and Soviet Union authority took a decision to produce nuclear weapons as soon as possible to, let's say, to balance the situation. And therefore, there was tremendous hurry in establishing this reprocessing plant and production of weapons-grade plutonium. Therefore, people didn't think so much about the environment and contamination. However, after 2 years of operation, it became clear that they contaminated very seriously Techa River and other aquatic ecosystem in surrounding area. So at the same time, the production was increasing all the time because the Soviet Union needed nuclear weapon and let's say accumulated the power of nuclear weapon. Therefore, the production of plutonium was increasing all the time. And therefore, the amount of liquid radioactive waste was also increasing. So, in 1951, it was clear that such a technology contaminate environment, and but amount of radioactive waste is increasing. Therefore, the decision was taken to discharge liquid radioactive waste, again, low and intermediate, because high-level radioactive waste were discharged to special tanks, very big tanks, located underground. The technology was quite similar to Hanford site in US. And but low level and intermediate level radioactive waste, which is still very radioactive, was discharged to Lake Karachay. Lake Karachay is located on the side of Mayak, inside, not outside. And therefore, nobody from population have access there. Only professionals have access. So during a long time, so the radioactive waste, low and intermediate level, was discharged to Lake Karachay. So this is about the first source of radioactive contamination in Mayak. And second source to Lake Karachay. Then I told you that high-level radioactive waste was discharged to special big tanks located underground. In September 1957, one of these tanks exploded. So, but this was not nuclear explosion, or there was nothing dealing with nuclear or radioactive. So the liquid radioactive waste is quite specific liquid, quite reactive, and and exothermal reaction happened in this tank with release of huge amount of energy, huge amount of heat. So the energy released in this reaction was so powerful that explosion removed the probe of the tank, and a large amount of the radioactive waste was released to the atmosphere and then deposited to the land. And here you can see the trace of this accident. So actually the explosion was very immediate. It was immediate, and therefore the atmospheric transport was happened just according to the wind direction at the moment of accident, and the position represent very narrow trace in the direction of wind at the moment of explosion. Actually, this trace is about 300 kilometers length. And here you can see the isolines of strontium-90. So this was the most important ecologically significant radionuclide, which was released during this accident. And this trace is called now as a South Ural radioactive trace. Another thing I would like to mention, that Mayak is located over here on Techa River, and Techa River is part of a big, large basin of Ob River, which is finally entering the Arctic Ocean. Therefore, the concern is how serious is effect of Mayak radioactive contamination, and is it possible to reach Arctic Ocean, or how far the radioactive contamination disperse from Mayak. So this is about the radioactive contamination of Techa River, which I mentioned briefly. So the environmental monitoring of activity levels in the Techa River started in 1951. So here you can see two reservoirs, R3 and R4. Actually, these reservoirs were the discharge points of radioactive, liquid radioactive waste. So after 1951, as I told you, it was recognized that this is a serious challenge for the environment, this radioactive waste. So actually, a big part of radionuclides was settled down on the bottom in reservoir 3 and reservoir 4. But even remaining part was very significant. So the decision was taken to create very large reservoir to increase the settling down of radioactive particles on the bottom. And in 1956, another large reservoir was constructed with a dam to prevent the dispersal of radioactive materials through the Teche River. And actually, this construction reduced substantially the flow of radioactive materials through Teche River. But still, there was some residuals. So later, in 1963, I think, another additional reservoir was constructed, which is Reservoir 11, and this is Reservoir 10. So these reservoirs were constructed with the only aim to prevent radioactive material dispersal through Teche River. So they didn't have any, let's say, electric power significance or any other. They were established with the only purpose to stop the river transport of radioactive material. Yeah. So sources of radionuclides are now limited to leakage of water through the banks of the bypass of channels, the body of dam 11, and the bed of reservoir 11. Actually, this is the only way now to disperse the radioactive waste. And here you can see again the river system. This is the Teche River. These are these reservoirs. And this is the Ob River basin. So this graph is very well describing the impact of Mayak radioactive waste transport on the river water. Here you can see, let's say, yeah, this is here the point of Teche River mouth. And here you can see the activity concentration of strontium-90 in becquerel per cubic meter. So the data correspond to the, let's say, 2005 to 2007 years. This is, let's say, about 50 years after the accident and almost 60 years after Mayak starting to work. And you can see that the concentration dropped down during the, let's say, transport by river system, but still substantial until Irtysh River mouth. Irtysh River mouth is entering to Ob River. So the length, the distance of this distance correspond to about 1,500 kilometers. So 1,500 kilometers away from Mayak, we still feel it. So, by the way, 1,500 kilometers is the length of Japan from the south to the north. So this is a huge distance. But of course, strontium is relatively mobile radionuclides. Radionuclides like cesium-137 or plutonium and many others, they are not able to be transported for such a long distances because they are very strongly bound by sediment particles, settle on the bottom in the reservoir or stagnated areas, and stop to be transported. Okay. Okay. So this is Lake Karachai. I told you the Lake Karachai was another point for discharge of low-level and intermediate-level radioactive waste at Mayak. Lake Karachai is located on the site of Mayak, inside the industrial site. Originally, it was a small, shallow natural lake. So since 1951, the lake has been used as a repository for intermediate and low-level radioactive waste, replacing the previous practice of discharging waste only to Kecha River. And here you can see, let's say, development, the situation with Lake Karachai. I would like to say now that Lake Karachai was probably the most contaminated lake in the world. However, now it doesn't exist anymore because the huge remediation program was taken by Rosatom, and the lake was fulfilled with gravel and stones and cement blocks, and then completely covered, so it doesn't exist anymore. And the dose rate is more or less normal over there. However, the problem with groundwater is still there because in the lake there was huge amount, huge storage inventory of radioactive materials. And they, of course, infiltrated through bottom of lake and appeared in groundwater aquifers below the lake. Especially, this is important for mobile radionuclide. And here you can see two maps of groundwater contamination by strontium-90 and cobalt-60. These are two very good examples of mobile radionuclides which are transported very well in solution. And here in the center, you see Lake Karachai itself. And here you can see how huge is the area of the effect on groundwater. This is for strontium, and this is for cobalt. So, and this problem, of course, being in groundwater, these radionuclides are transported farther, and this is a serious problem for surrounding areas because many people use the groundwater as a source of drinking water, and so something should be taken for this as well. So, Kishtim accident. Actually, I briefly told you about the thermal explosion, which happened at the tank in 1957. About 740 petabecquerel of radionuclides was actually released during the accident, but about 90% were deposited on the site of Mayak, and only 10% were transported outside Mayak itself and formed this trace, which is about 300 kilometers long in northeast direction and about 30 to 50 kilometers width. So, main messages about Mayak. Oh, I think I take some more time. I will try to hurry up. So, dispersal of radioactive materials from Mayak to the environment led to harmful effects on the environment itself, restriction on land application, relocation of inhabitants from a number of settlements, and observed health effects on human populations. The radionuclide of main concern is strontium-90, as it is remobilized from soils and sediments to much greater extent than cesium-137 and plutonium isotopes. Increased contamination of groundwater, in particular strontium-90 and cobalt-60 from Lake Karachay, is of serious concern still. To avoid the transport of contaminated water down the Teche River, huge reservoirs were constructed in 1956 and 1963. A rehabilitation program to fill in Lake Karachay has been completed in 2015. The first surface area of the lake has been reduced from half square kilometers to 0 in 2015. So now Chernobyl accident. Chernobyl accident is still the most severe nuclear accident in the history of nuclear era. As a result of Chernobyl accident, about 85 petabecquerel of cesium-137, 54 petabecquerel of cesium-134, 1,760 petabecquerel of iodine-131, 10 petabecquerel of strontium-90, and 0.07 petabecquerel of plutonium isotopes were released into the atmosphere and transported over the long distances. So here are the causing events and processes which let's finally ended at the Chernobyl accident. So it took place 26 April 1986. Prior to accident, the reactor had been operated for many hours in non-design configurations. in preparation for experiment on recovery of the energy in the turbine in the event of unplanned shutdown. The cause of the accident is rather complicated, but can be considered as a runaway surge in power level that caused the water coolant to vaporize inside the reactor. This in turn caused a further increase in power level with the resulting steam explosion that destroyed the reactor. The graphite burned for many days, and releases of radioactive materials continued during 10 days until 6 May of 1986. So here you can see the radionuclide source stem distribution per day. So during the 10 days, there was a release, and then you can see was tremendous drop down. So during the 10-day release, the wind direction changed tremendously. Actually, the wind turned for 360 grad during the period of the release. And this is why the trace of Chernobyl accident is so different from Kyshtym accident, where the release was immediate and just reflect the wind direction at the moment of the accident. And here, during 10 days, you can see here the map of Europe with the cesium-137 deposition. So you can see many spots everywhere, even in Scandinavia, UK, Italy, Germany, and so on. But of course, 3 major republics were mostly contaminated. These are Belarus, Russia, and Ukraine. By the way, at the moment of the accident, these 3 republics were part of Soviet Union. So that was the same country for all of them. So here you can see how the wind direction changed. First plume was to the northwest, then west, then east, then southeast, south, and southwest. And therefore, actually, the whole circle was down by the wind, and this created very exotic trace and spot. Together with wind, another factor is extremely important. These are precipitation. Because when you have precipitation during the radioactive cloud passing through, you have much more efficient deposition, because wet deposition is much higher efficient than dry deposition. When you have precipitation, during the passing the cloud, you can expect deposition of radioactive materials. So in this respect, they explained the deposition in UK, in Cumbria, in Italy, and in Germany, and also the Tula Areol spot of Chernobyl trace is also explained by higher precipitation in the area during the passing the cloud through this area. So that was cesium-137. Cesium-137 is a semi-volatile radionuclide, so it's evaporated during the accident at the temperature of the accident. But refractory elements such as strontium and plutonium, they were not evaporated and they were released together with nuclear fuel particles or nuclear fuel debris. They were incorporated in this debris. These debris were heavy. The density of nuclear fuel is quite high. And also they have quite significant size. Therefore, these particles were deposited mostly near the nuclear power plant. For example, here you can see the plutonium. Most part of plutonium were deposited inside the 30-kilometer zone. Similar situation with strontium, only partly it was transported outside the 30-kilometer zone. So, fuel particles is distinguishing feature of the Chernobyl accident. And the dominant part of radionuclides deposited on the soil surface in the Chernobyl nuclear power plant vicinity was incorporated within fuel particles. Even cesium-137 and cesium-134, 75% in 30-kilometer zone were incorporated inside these fuel particles. However, outside 30-kilometer zone, for example, in Western Europe, mostly condensation particles were deposited, which were much more radionuclide in these particles were much more soluble, and as a result, more bioavailable. Particle dissolution was the key process governing radionuclides mobility and bioavailability in soils during first years after the accident. So, Chernobyl cooling pond. You can see here the map of Chernobyl cooling pond. And this water body is, of course, one of the major water bodies that were heavily contaminated as a result of the Chernobyl accident. The cooling pond was used as a reservoir for cooling water for Chernobyl nuclear power plant reactors until 2000, when the plant was finally shut down, and the cooling pond became no longer required for operational purposes. In May 2014, actually 14 years after shutting down, water pumping from Pripyat River to the cooling pond was stopped, and as a result, the water level in cooling pond began steadily declining and was reduced by more than 6 meters. This is because level of cooling pond was higher than Pripyat River, and water from Pripyat River was pumped to cooling pond to keep it alive. So here you can see the picture of the cooling pond after water level dropping down. And you can see a part of the bottom sediments exposed to the air. This is sands. So by now, fuel particles have been almost completely disintegrated in terrestrial soils. However, due to low dissolved oxygen concentration and the high pH, dissolution of fuel particles in the cooling pond sediments was significantly slower than in soils. As a result, in the cooling pond sediments, the prevailing part of strontium-90 activity occurred in the form of fuel particles still. After water level dropped down, part of bottom sediments exposed for atmospheric oxygen, which accelerated fuel particle dissolution and radionuclide remobilization. So, main messages about Chernobyl. Chernobyl accident in April was the most severe nuclear accident in the history. Release of fuel particles as a result of Chernobyl accident decreased radionuclide mobility and bioavailability, especially in near zone. Radionuclide wash-off and river transport are the most important process of post-accidental radionuclide spatial redistribution and secondary water contamination. Similar to Mayak area, dam reservoir play a role as traps for radionuclides and contaminated sediments. Okay, now we go to the Fukushima Daiichi nuclear power plant accident, which happened in March of 2011 as a result of Great East Japan earthquake, which caused a huge tsunami. And then this is the Fukushima Daiichi nuclear power plant before the accident. This is how the tsunami happened. Of course, there were several designing errors in case of Fukushima Daiichi nuclear power plant. First of all, before the construction of nuclear power plant, there was a wall. There was a wall over here with a height of 30 meters. It was cut away just to make simpler the transport of materials to the nuclear power plant. This is first. So, second, the TEPCO, the company, nuclear company, which owned the nuclear power plant, constructed the anti-tsunami wall. You can see it here. The height of the wall was 5.7 meters. So the tsunami wave was about 15 meters. So tsunami wave easily took over this wall. Why they did so? Because they look at the history, and the highest wave of tsunami in Japan was about 5 meters, according to the records. So they made it 5.7 meters. However, in reality, the height of wave was much higher. Then the next error. So, of course, earthquake destroyed the power line. Of course, the electric power is important for operation of nuclear power plant, and including the pumps which provide the cooling water to the reactor, they work on the electricity. Of course, nuclear power plant has generators, and they automatically switched on after the earthquake and destroying the power line. But this generator were located on the knees of the building of nuclear power plant. Moreover, the building was not properly hermetized, and therefore the generator were flooded, covered with the water, and destroyed, were broken. So no power, no pumping. So as a result, we had an accident. This is the Fukushima Daiichi nuclear power plant after the accident. And this is the trace of Fukushima Daiichi nuclear power plant on the Honshu Island in Fukushima prefecture, mostly. But fortunately, so 80% of the release were transported during the several days of release in case of Fukushima Daiichi nuclear power plant accident, were transported to Pacific Ocean. And only 20% of radioactive materials were deposited on the land. 80% were transported to the Pacific Ocean, deposited, and was a small addition to global nuclear weapon tests fallout in the Pacific Ocean. Pacific Ocean is huge amount of water, dilution is huge, and actually only in the near area of Fukushima Daiichi nuclear power plant, the not some substantial increase in cesium concentration was recorded. Okay, this is the comparison of Chernobyl and Fukushima in the same scale, by the way. And you can see here that the levels of contamination and deposition are comparable, but the area of contamination is, of course, much smaller in case of Fukushima. So, important part in the behavior of radionuclides in the environment is speciation of radionuclides. So here you can see the comparison of speciation in 3 different contaminated areas. First, in case of Kyshtym accident or Mayak, we had soluble, mostly soluble radiocesium compound. In case of Chernobyl, we had fuel particle, nuclear fuel particles, which are destroying with time scale of about 2-3 years. In case of Fukushima, the substantial part of radiocesium was deposited in the form of glassy hot particles or cesium balls or cesium microparticles. And here you can see the pictures of these particles. This is the air filter. This is particles itself, and so on. So I must say that the decomposition of these glassy hot particles is much, much slower than even fuel particles in Chernobyl. The time scale of the leaching of radionuclides from this fuel, from these glassy hot particles, is more than 10 years, even 15, 20 years. So we found that the radiocesium in Fukushima is much stronger bound to soil particles, and therefore its bioavailability is lower. One of the reasons is these glassy hot particles, and another reason is that the soils in Fukushima prefecture are characterized by high ability to sob, selectively sob, and fix radiocesium. So this is about the catchments. Here you can see Chernobyl, and this is a Dnieper River basin, which was seriously contaminated, and therefore then the radionuclide contamination transported by the river. And here you can see the situation in Fukushima. So 14 basic catchments, including the Abakuma River. Abakuma River, which flows through Fukushima city. Okay, so actually the annual precipitation in Fukushima is 2 to 3 times higher than in Chernobyl and Mayak. Generally, higher precipitation, higher air temperatures, and steep slopes in the region promote higher wash-off of radiocesium and faster natural attenuation as compared to the Chernobyl. Here you can see the distribution of precipitation during 2 years. The maximum precipitation fall down during typhoon period. So here you can see the typhoon Eta, which happened in September 2015. About 450 millimeters were fallen down during several days of typhoon. Here is another example, Typhoon Hagibis, which happened in October 2019. Here, more than 400 millimeters were fallen down during a day. Very strong precipitation, which caused this kind of flooding. You can see here, this is Abakuma River near the house where I lived at that time. These floods, they, of course, redistribute the radiocesium deposition on the catchment and removed and moved the radiocesium to the ocean. So, main messages. Fukushima-derived radiocesium is stronger bound by soil and sediment particles as compared with Chernobyl, Mayak, and nuclear weapon test origin radiocesium. This promotes faster scavenging of radiocesium in surface waters and prevailing transport of radiocesium on suspended material with surface runoff and river flow. Higher precipitation in Fukushima region, steep slope, and higher average air temperature promote higher wash-off of radiocesium as compared to Mayak and Chernobyl cases, and faster natural attenuation of contaminated catchments. Extreme flood events during typhoons result in fast and efficient redistribution of radiocesium contamination in Fukushima. Similar to Mayak and Chernobyl, dam reservoirs in Fukushima play important role of traps and prevent radiocesium transport downstream. So at the end of my lecture, I just want to advertise our series of book. The first volume is devoted to Lake Karachai at Mayak. The second volume is devoted to Chernobyl, and the third one is devoted to Fukushima. These books are quite recently published by Springer. And finally, I thank you very much for your attention. And if we have a time, I'm ready to answer the questions.
Propose that we will have questions in private communications due to the time schedule. And now we will have a short coffee break. Okay.
Okay.
Okay. Thank you. Thank you very much.
Okay. You can share my email for questions. Да, пожалуйста.
Ага.
Так, да. А где моя флешка?
Thank you for this presentation. It was really interesting.
So, dear colleagues, let's continue. And I forgot to say it in the beginning of the today's morning that today we are celebrating the 80th anniversary of the Russian atomic industry in our country. So it's a great celebration, and there are quite plenty events and activities are planned. So, and we are continuing with the lecture from Sergei Mikheykin, who is the leading researcher in the Institute of Inorganic Materials of the Rosatom Corporation as well. So please, the floor is yours.
Good afternoon, dear participants. Today we will speak about decontamination. Two things of decontamination for decommissioning and the decontamination of soils, contaminated soils. Our institution is a part of fuel company 12, which are responsible for decommissioning activity in Russian Federation and in the countries of CIS countries. And our institution is a center of competence for development of decommissioning technologies. And in the framework of this activity, we developed the new methods of decontamination and dismantling technologies for decommissioning. And today we will discuss problems of decontamination. What we should need to know firstly about decontamination. Decontamination is a relatively simple thing, and we can compare it with simple washing of dish for after dinner, for example. But like you see in this slide, if we after dinner we have a interaction with relatively fresh contaminations, which cannot fix it on the surface. But in the case of the contamination of nuclear contaminations, we have practice and we have problem with fixed contamination, because all contaminations arise within many years or 10 years, and so many contaminations strongly fixed with surface. And for this purposes, we need to use a more aggressive material, more aggressive technologies. Оно не работает. Что-то оно не работает. Стоп, давайте попробуем. Нет, не хочет. Нет, вот так вот. Firstly, what we need to know about decontamination, we can subdivide the decontamination methods for two big parts. Decontaminations for maintenance and decontaminations for decommissioning. What's the difference? For example, when we have a problem with operated nuclear facility, we need to use just only simple techniques which can support of surface in the not destroyed media, because in this case we need all equipment should be reoperated after our maintenance, and so we can use just only soft technologies which can prevent which should prevent surface against corrosion materials, against corrosion. But for example, if we have a problem with decommissioning, we don't need to use just only soft materials. We can use more strong materials, more strong technologies, and we can destroy more surface. So we can remove more materials from the surface. So we can use a more wide range of technologies. Нет, давайте я буду отсюда управлять как-то, наверное. Или давайте мышкой буду. Так. Просто колесиком. Ага. What we need to know about contaminations. No. Sorry. Что-то не работает. Что-то оно не работает. Давайте, excuse me, попробуем. Contaminations. Здесь, да. This is picture, and so you can see the contaminations, how it looks really in a real environment. More important part of contamination. Так, лазер здесь, да? Лазер тоже не работает. Работает. Don't work. Так, давайте посмотрим. Может, батарейка работает. Почему? Почему она работает? So. Вот. So, this is a contamination environment, contaminated environment. This is metal. So, when we have a problem with sediments, we can subdivide the sediments for 3 categories. The first of all, it is real sediments from the water environment usually. Then metal oxide layer, which oxide layers or carbonates, and then contaminated metal. So for remove следующий slide. So for removal of contaminations, we need to remove all these layers, because contaminations usually accumulated in the surface of metal and incorporated into the oxide layers, because oxide layers is a very good sorbents. So it's accumulated all material, contaminated contaminations inside all environment. And so you see it looks like a multi-layer cake. It's for example, pipes from the steam generator. And so it is subdivided for few contaminated layers, which we need. So if we will remove contaminations, we need to remove all this layers, layer by layer, with different aggressive materials or aggressive techniques. Следующий слайд, пожалуйста. We need to subdivide two types of contaminations. It's weakly contaminations, which you can remove very easy. It's usually result of physical absorption with energy absorption no more than 42 kilojoule per mole, and chemosorption. It's more strong contaminations, which so if we can remove the first kind of contaminations with very simple methods, wipe mechanical methods, but for removal of chemosorption contaminations, we need to apply more aggressive materials, usually chemical solutions, very aggressive chemical solutions for removal of this material. So energy of interaction with surface is more than 42 kilojoule per mole. It is very simple subdivision of these contaminations. So следующий. Oxide layers, it's a very complex material. It includes a very different combination of oxides. For example, for carbon steel, it's just only ferrum oxides. But in the case of stainless steel, it's oxides of ferrum oxides or chromium, chromite, or combination of chromites and manganese and other materials, so which incorporated in the composition of stainless steel. Следующий, пожалуйста. So decontamination. Следующий. Там есть. Ага, да. Decontamination is a full or partial removal of contaminants by physical, chemical, or biological methods, with the application of any methods. And следующий. It's very important to note that it's impossible to use some universal method. It's no universal method, so it's no single techniques for address of all kinds of problem. We should apply different methods for decontamination because the contamination choice of decontamination methods depends on many factors and depends on the type of facility, power plant, industrial facility, or accidental contamination, research center, isotopic composition, level of contamination, chemical states, material of equipment. And more important that optimal decontamination techniques is cost-effective removal of contaminants with minimal exposure of workers. So it's a main task of choice of decontamination techniques. Следующий. Basic principles for choice of decontamination techniques. Decontamination techniques should be very single for application of this objects. More important is the safety. Safety because the contamination activity is the activity for safety of object, for safety of workers, safety of environment, and so safety is a more important thing in the choice of decontamination techniques. Efficiency, of course, very important for productivity of decontamination methods and for its cost. Because economic efficiency is also very important, because you know that it's really it's possible to apply very strong and aggressive decontamination techniques for the full decontamination of surface. But in this case, you can receive a lot of secondary radioactive waste. And so we can, then the secondary radioactive waste should be treated, collected, treated, and stored after that. It is a very high cost of this activity. And so the choice of decontamination methods is a balance between cost of treatment of surface and cost of treatment of secondary radioactive waste. What is very important? Which cost is the best? So with waste minimization principle is very important because we can produce a very big amount of secondary waste, but it's very costly activity. And availability of methods should be labor intensive, difficult to manage, and or difficult to automate because it's technology now available to apply automatically or with the use of remote control techniques. Следующий. So in this picture you can see the main principles of decontamination techniques. So it's a main activity we need to calculate when we will choose of decontamination techniques. Следующий. Main factor which we need to apply for comparison of different decontamination techniques is the decontamination factor. What is it? It is a ratio of initial activity of contaminated surface to final activity of the surface. It is not important. It is not very important. What we can use it's dose rate or specific activity, because it is the contamination factor. It's just only digital. It's no physical nominations, but the contamination factor, it's very played for purposes of comparison of different decontamination techniques. And the very high decontamination factors can occur in the case if we will apply decontamination for very highly contaminated materials. So because it's very easy to remove high contaminations, but it's very difficult to remove very small contaminations. It's a very interesting thing, but it's need to know when we will discuss about the contamination factors. So the contamination factor is not a magic number for qualified decontamination techniques, but it's relatively usable methods for comparison of decontamination techniques. Следующий, пожалуйста. Main types of decontamination. Historically, the first methods for decontamination was used is the chemical decontamination methods, and now it's a lot of decontamination methods developed up to now, and it's really widely applied for decontamination purposes. And the next one, and all this decontamination techniques are based on the chemical interaction between chemical solution and contaminated surface. And as a result of this decontamination activity, all contaminations incorporated in the oxide layers or metal surface is diluted in the process of chemical reactions and then transferred to the water media, usually to water media, and then removed from the surface. But also we can use non-chemical methods. It's mechanical methods, just only treated for on the basis of crushing of surface, because in the result of mechanical attack to the surface, we can crush it, contaminated surface, contaminated layers also, and remove it from the metal surface. Следующий, пожалуйста. This is the key decontamination methods: blasting or steam water methods. Washing, it's more easy, it's a washing process, because it's need just only water or small surfactants, small amount of surfactants, but it's responsible just only for the contamination of fresh contaminations. It's not operated for the strongly fixed contaminations. Melting, mechanical actions, electrochemical actions, chemical actions, heating. Sorry, it doesn't work. Excuse me. Следующий. So here you can see the list of main decontamination methods: chemical process, chemical films, gels, melting, decontamination of molten salts reactors, mechanical abrasives, lasers, and the big parts and big blocks of chemical processes are subdivided for many types of chemical decontaminations, and we will discuss a little bit later. Следующий, пожалуйста. two main approaches to decontamination. Decontamination for decommissioning purposes. Decontamination before dismantling and decontamination after dismantling. It is subdivided for two big sections because in the case of dismantling before decontamination, we can apply not very big amount of technologies because we can apply just only for equipment in wall before dismantling, before cutting of material. So we can use just only for big equipment on site. But in the case if we can we can apply the decontamination methods after dismantling, we can use it for cutted materials. We can use the very big balls or apply to the glove boxes for decontamination for cutting materials. So we can apply different methods for decontamination, and now we will discuss which methods we will use. Следующий, пожалуйста. The first and very big block of decontamination methods is the chemical reagents. Chemical methods suitable for complex geometry. It's applied for both methods for before dismantling and after dismantling. It's have reach a very high decontamination factor up to 10 and 4 for the contamination purpose. It's very important because it's produced not too high amount of not so high amount of secondary radioactive waste because we have a very strong big decontamination factor. It's possible to combine the contamination methods, the contamination reagents, so for purposes of decontamination for all types of radionuclides, because you understand that the contamination of different types of radionuclides and contaminations, we can apply different chemicals for desorption from the surface, for complexation of in the water media, and so on. And chemical decontamination methods is a well-known practice because it started, application of this method started in the middle of 15th maybe, or early. And so it very good experience accumulated in this area. So, but disadvantage of this method is a relatively big amount of aggressive secondary waste, because for the contamination we apply strong acids or alkali solutions, and for treatment of the solutions, treated solutions after treatment of the surface, we can apply very strong methods for treatment as radioactive waste, because all this media is very strongly contaminated. Следующий. For choice of decontamination methods, we can apply different different combinations of reagents, and for selected that following conditions are met: rapid and complete wetting of surface, because you know that all interaction in the chemical reactions are in the water media. It's the best choice in this case. And destruction of the bonds between the radioactive substance and surface, and should be very strong in this case, because we should remove all these contaminations from surface. And prevention of resorption. For prevention of resorptions, we can apply special additives like complexons, which can prevent resorption of radionuclides or heavy metals from the transuranic radionuclides, for example, from water media to to surface. Следующий. Again, we repeat idea that we can apply two methods of decontamination. Soft decontamination, which we can use mild chemicals. It's applicable for decontamination of, for example, radiochemical equipment during operation, or equipment for NPP during maintenance works, for example, for steam generators, or decontamination of other reactor materials, or aggressive chemicals. Aggressive chemicals usually used for decommissioning purposes, and we can apply very strong materials, like with very strong temperature. It's around 100 centigrade, because the speed of chemical reactions very high in this area. So we can apply very strong chemicals with strong temperature. Следующий. For this purposes, when we apply decontamination methods, chemical decontamination methods, we can subdivide. This is curve is the solution of contaminations from the surface. 0A, parts of 0A, it is responsible for the contamination of sediments, or very simple sediments on the surface. And so it's a very speedy part of this curve. And then process is stabilized, and this process of dissolution of strong deposits and oxide layer. And then it's practically plateau. We have reduction of speed of dissolution of surf contaminations, and this parts of curve are responsible for dissolution of metal surface. So it's very easy to understanding this dependence of degree of decontamination on the process time. So we can stop the contamination methods at any moment, but we can understand which part of this curve we will reach before this, before our action. Следующий, пожалуйста. Chemical solution. Many combinations. We can apply very simple methods, just only with one reagent, for example, nitric acid, or can apply combination of chemicals, for example, chemical for nitric acid with permanganate, for example. But we can combine not only one method of acids, but we can combine two methods. We can apply two methods. Alkaline first alkaline stage of decontamination, which alkaline method is responsible for transformation of chromium oxides into the soluble form. And then we can apply for cleaning of the surface, or for polishing of the surface. We can apply excite methods. For it, it's two stage methods we will use for decontamination of strongly contaminated, or mainly stainless steel, for decontamination of stainless steel. Следующий, пожалуйста. Here you can see example of chemical reactions which are in the result of chemical interaction between exit solutions with surface. Here it is very interesting publications, but this is book is just only in Russian. named author is Ampilogov. It's very old researcher of Russian chemistry, and if you can read in Russia, you can find this book and more interesting information about the contamination methods into this and the basics of the contamination methods includes in this book. Next slide. This continuation of this chemical reactions. So you can see that the reactions, that's the main idea of the solution surface. It's a transfer or strong contaminations, heavy contaminations to soluble form, which can be removed with water solutions. Yeah, I think you will have this presentation, so you can have this information here later. Next slide, please. Next 3 slides is just only for information. It's a combination of chemical solutions. You can see that it's a very big choice of the contamination solutions is now. Really, it's available. It's subdivided for the contamination methods for temperature and for different purposes, for stainless steel and for carbon steel. For different kind of equipment. Следующий слайд потихонечку перелистайте просто. So you can see that this table, it includes a lot of methods, just only for your information. And here you can see just information about application of chemical decontamination methods in situ. It's a good example of decontamination before dismantling. For the contamination of steam generators. And so you see the list of the contamination chemicals which you can apply for the contamination methods. For this purposes, steam generators includes in the old cycle of the contamination, the pumps then treated for few cycles of the contamination method, for the contamination solutions, and with high velocity and relatively high pressure. It's pumping this water solution to steam generator and remove all contamination from the steam generator pipes. And for this purposes, it's mainly European application for the contamination methods, CORT ultraviolet process, and the MEDOC process. It's mainly, it's very old methods, but operated still now. It's have good results for the contamination of reactor equipment before dismantling. Следующий слайд, пожалуйста. Next variation of chemical solutions methods is the application of ultrasound. Ultrasound can activate chemical reagents into solutions because when we apply a high frequency of ultrasound with frequency range between 20-40 kilohertz, we can activate all the contamination processes up to time 2-3 times. Here in this curve you see this is blue curve is red curve is the contamination without application of agitation with ultrasound, and blue curve is the contamination with application of ultrasound. You see activation is practically 2-3 times in practically the same conditions. Следующий, пожалуйста. The same, also, да, этот. Also, we can apply activation of for chemical reagents. It's application of electrochemical decontamination or electropolishing process, other name of this process. Electrochemical decontamination apply electrical potential to this media, and we can apply low voltage and high power electricity power to in the water solution of, for example, phosphoric acid here, and then we can remove just with application of current on the surface. We can remove not only chemical oxides layers, but also thin layer of metal from the surface. It's an application of for 100 microns or up to 1 millimeters of surface we can remove with application of this methods. It's this methods next. Следующий, пожалуйста. This methods can apply in two applications, into the base and the chemical base. So you can just only place your contaminated equipment in this base and then starting this process, or you can apply external electrode like here, which can fit it with fitting with electricity, and then treated the surface of the materials. Следующий слайд, пожалуйста. If we will apply external electrode, you see that it's like here, cathode anode from this tool, chemical tool, this tool, and then all reactions occurs in this water media, in the media between your tool and contaminated surface, and then you should remove just only thin layer of this liquids with some kinds of trash or special like vacuum cleaner. You can remove from the surface. So in this case, you will have a very small amount of secondary radioactive waste as liquid, because very important to note that this method is very efficient, very quick, but secondary waste is the chemicals, very strong chemicals, and with secondary wastes of heavy metals from all carbonates or other reagents, which can normally it's very difficult to treat for as a secondary radioactive waste. Следующий, пожалуйста. This is combination of ultrasound and electrochemical methods applied for the Bogunitsa nuclear power plant. So it's more so you can see it's possible to combine different methods for one application. Следующий слайд, пожалуйста. Forms. It's very interesting methods, application of forms, because it's also we have reaction between chemicals in water media, in surface in water media, but in this case we have a very small amount of secondary wastes, because it's main target of the forms is transporting of chemical reagents to contaminated surface. Then when these forms will collapse, we can collect it with vacuum cleaners, and just only will have just only small amount of secondary waste. Следующий, пожалуйста. Next, very interesting block of chemical methods is application of strippable polymeric coatings. The process you see that is we can remove contaminations with very thin layer of polymeric films, but normally, следующий слайд, пожалуйста. Так, скачать какой-то слайд, похоже, нет. Значит, потерялся. Все. Normally, this polymeric films treated with water solution. Usually, for application of polymeric films, we use polyvinyl alcohol, and it is water solution. And so, after polyvinyl alcohol, we can include special chemical additives which can dissolute surface contaminations, and then after formation of polymeric films, all contaminations includes in this polymeric film, and then we can remove this polymeric film from the surface with fixed contaminations. And just only this very thin polymeric film, the thickness of this polymeric film is just only a few hundred of microns, so we can remove it just only a small amount of secondary radioactive waste. It's very interesting methods of decontaminations. Следующий, пожалуйста. It's variation of polymeric films. It's application of destroyable gels. Gels also applied to the surface from the water solutions, and then after fixation, after reaction of this surface, and after drying up of these materials, gels auto-destroyed for small items and can remove from the surface with just only vacuum cleaning. In this case, we have not we have problem just only with solid radioactive waste. We have no liquid radioactive waste, secondary radioactive waste. Следующий. Next block is a block of mechanical methods. Mechanical methods is the contamination methods which based on the mechanical destroying of the surface. And in this case, we should know that more important thing it's not only destroy the surface, but remove all small crashed materials or dust, radioactive dust, aerosols from the surface with vacuum cleaner. Like here in this tool, you can see this special blades separated with the surface, and immediately all products of this destruction of the surface is immediately removed with vacuum cleaner, then treated from the HEPA filters for treatment of cleaning of air. Next, please. It is different kinds of materials. It's scabbling applicable for concrete or bricks or ceramic or different different materials. Следующий, пожалуйста. It is needle scanning. It's also materials, but also mechanical methods for the contamination. But it's very important because the needle, each needle moves independently. We can treat very difficult design of surface, like here, because each needle comes to the surface independently and treated very complex geometry. We can treat very complex geometry of surface. It's a very interesting method for mechanical decontamination. Next, please. Laser decontamination based on the destruction of surface with laser beam, because it's a surface, it's need micro explosion of the surface occurs after interaction between the laser beam with the surface, and this this explosions destroys the surface, and we can also remove the surface layer with some different vacuum cleaners for treatment for secondary radioactive waste. And so you can see treated, just only destroyed, treated with, here as you can see example of concrete, also applicable not only for concrete but for metal, for bricks, for ceramic, for different materials. Now it's very widely applicable methods for cleaning of surface. Следующий, пожалуйста. Blasting decontamination, it's a very easy method for application because it's we can use different blasting materials as mineral steel pellets, ceramic, plastic pellets, or carbon dioxide or dry ice. Next, please. For example, see the full cycle of decontamination methods, because you see after application of abrasives, we can collect it, separate, use it things after from the new one, add the new one abrasives, and then recycle all the spray methods, or recycle these abrasives again. It's very suitable methods, but very big disadvantage of this method is creation of very big amount of secondary radioactive aerosols. So we need to apply very specific methods for protection or isolation of process. For example, apply these methods in the glow boxes, for example, for isolation against from the environment. Следующий, пожалуйста. Dry ice methods. It's also kind of abrasives methods. It's very good because it's the advantage of these methods is absence of secondary radioactive waste practically, because dry ice evaporated immediately after application, and so we will have problem just only with sediments created after destruction of contaminated surface or destruction of sediments on the surface. And следующий, по-моему, последний слайд будет. Pressure water jet, practically the same as abrasives, high pressure water with high temperature and high pressure water. Следующий. And mechanical decontamination, you can apply very simple and easy methods, just only with handy treatment of surface for reduction of not fixed contamination. And следующий, последний. Thank you for your attention. Так, у нас как следует, потом сразу вторая лекция. У нас, да, без перерыва. Так, давайте следующую. Just only for 1 minute for relax. Что-то букс. Да. Are you ready? Short relax. The contamination of soils. This presentation will be a little bit shorter, so we should be keeping time. Следующий. Contaminations of soil normally happen just only as a result of nuclear accidents, because in the process of normal operation of nuclear facilities, we have no problem with contamination of surface. If we have contamination of surface of soil, we have problem with safety of our nuclear facility. And of course, you know the main problems of main contaminated areas: the Chernobyl area, Fukushima area, Mayak site area, and also many contaminated sites happened during the long-term operation of nuclear facilities like Mayak site, again Sellafield site in Great Britain, or Hanford site in United States, or other small accidents happened in our history. And as a result of a nuclear accident, soils contaminated with different kinds of radionuclides. Combination of radionuclides depends on nature of your nuclear facility and materials which was contaminated, was exposed to the environment. And during the first time after accident, upper layer of soil, usually it's 1 or 5 centimeters of topsoils contaminated with radionuclides. Then this contaminations penetrated inside the top layers of soil and fixed in the horizon of 1 or 10 centimeters of soil surface. So we have the main idea for the contamination of the soil. If you start your decontamination activity early, you should remove smaller amount of radioactive soil from the surface, because if you will start it later, the contamination will penetrate deeply in the soil, and you need to remove more soil from the surface. Следующий. So what kinds of contaminations happened to the soil surface? Hot particles. Hot particles, it's particles of spent fuel or debris of reactor equipment. So very highly contaminated. A lot of hot particles happened in the Chernobyl fallout and the Chernobyl area. And all these hot particles was contaminated strongly with uranium and transuranium materials. It's a very dangerous particles, very highly activated. Then condensates of sediments of cesium, strontium from the atmospheric precipitations. This also happened in the Chernobyl area, and also happened in the Fukushima, after Fukushima accident. A lot of cesium contaminations happened in the Fukushima region, and also after Chernobyl, cesium contaminations comes from the Ukraine to Belarus to Russian Federation and to European part of to the European countries. And next is the penetration of liquid radioactive waste of different composition with soluble form for radioactive materials. It's happened if we will have some leaks from the radiochemical equipment in the radiochemical facilities. Следующий, пожалуйста. After penetration of contaminations to soil, it started to the very complex interaction between radionuclides and soil. Here you see the whole list of this materials. So one kind of reactions comes to the deeply penetration of radionuclides inside top layers of soil. Other one was leaching or volatilization of radionuclides comes to the transfer of radionuclides from the surface. Also, it's not noted here dust creation and also can remove the contaminations from the surface. And so strong wind, for example, in the Chernobyl area, resulted in the few times resulted in the contamination of surface by removal of a strongly contaminated top layer from the surface. Yes, this contamination then secondary transferred to the other parts of regions, but these layers of soils were decontaminated after strong winds. Следующий, пожалуйста. Можно следующее дальше. Methods of decontaminations. Soft methods is practically without removal of soil from the surface. It's a deep plunging. Later I will show you this photo. For just only for mixing of top layers of soil, and it's not really decontaminate methods, but can reduce those rates from the surface, because highly contaminated materials on the top layers, which created the main parts of dose rate from the surface, it's placed to the deep layers of soil, and then when blocked with a few tens of centimeters of layers of soils, and so dose rate will be reduced. It is also kind of decontamination, but it's not removal of the contaminated material from surface. It's just only mixture of soil. And strong decontamination methods, practically all of them depends on and all these methods is removal of surface from the remove this material, contaminated material from this site, and the treatment of this soil for different facilities we'll discuss later. And radiochemical separation, just on segregate different kind of removal of the surface soil. Следующий, пожалуйста. И следующий. So, very easy method of decontamination is excavation of topsoil. Very easy, just only you can remove contaminated soil up to clean soil layers. You will remove it and collect for next stage of treatment, like here, collect on the big bags for treatment and for storage, for preliminary storage, or for treatment of the chemical hydroseparation or other methods of decontamination. Removal of the surface can be with excavators or with machines or by hand. It's depends on your needed capacity of process. Следующий. Deep plunging of methods, you see I talked before. You see, just only you will not remove the surface of soil. You will not remove soil from this area, and you will not collect radioactive waste. Just only mixed of this layers of soils, the deep layers. Следующий, пожалуйста. Segregation. The block of this decontamination methods is a segregation by radiometry Оставьте пока. By radiometry density or size. Here you can see it's not soil, but it's an explanation how we can remove just only a contaminated area from this radioactive materials. This is photo from waste storage facility of Kurchatov Research Institution in Moscow. When we applied gamma visualization method, gamma visor, for visualization of strong contaminations, because if you can remove strong contaminations like here, you can reduce those rates for all surface and for all this object, and then you can we will work in more friendly radioactively friendly atmosphere here. And so next, пожалуйста. And this methods applicable for subdivision of the contaminated and clean soils, because not soils of cleaned contaminated like one things. It's because you see it's a porous system, and all different particles contaminated, not like one particle. So here contaminated soils combined soil pile, contaminated soil pile, then loaded to the belt of here you see placed detectors, gamma detectors, can operated after some limits which agreed with operators. All this detector operated if we have high activity, then operated the limits of this detector. Detector operated this belt operated for contaminated area, and so this belt operated to and will transfer this materials for contaminated area, and this area will accumulate contaminated soils, and then if we will have contaminations low limits, less than limits of this detector operated, all materials will comes to the clean zone, and all this clean materials can use again for refilling of material, refilling for dumps or other materials. We will not need to treat it like secondary radioactive waste. Следующий, пожалуйста. Here it is an example of segmented gate systems operated to the Sandia National Laboratory. Like here, this is other view, practically the same picture. Monitor, you see this is radioactive waste combined here to the drums to the container for radioactive materials, and clean soil comes to the reclaimed clean materials. Следующий, пожалуйста. Just only a real photo of the segmented materials. By this methods was treated more than 99% of clean materials were refilled to this against to the site. And next. And that's very interesting because here we treated 3 sites. It collected 3 different amount of volume of contaminated materials, contaminated soils for Sandia laboratory, and after treated, we reduced this amount of the soils were treated. You see, to the few hundreds times less. So for treatment of for radioactive waste was sent just only small amount of secondary radioactive waste, secondary radioactive solid soil. Следующий, пожалуйста. Practically the same picture is equipment operated at the Bogunica site, Bogunica nuclear power plant in Slovakia. Practically the same idea, but not but smaller scale of this facility, because it's just only a few tens of cubic meters of treated cubic meters of contaminated soils were treated for this facility. The idea is the same: a conveyor, detectors, and a few in the two placed materials. For one materials is radioactive materials, and second materials is just only for clean materials, clean soil. Следующий. Можно следующий опять. This is just only parameters of the facility. The next idea. No. This is the same idea for radionuclide separation of materials, just without application of any special mechanism, any special facilities, just the application of an excavator, measurement of activity in this in the excavator. You place this excavator for two detectors, like here. Important things that the thickness of this layer of soil should be standard for standard for formation of for standard dose rate measurement methods. And if we'll have a result of measurement of this contaminated soils less than it's possible, all the soil send it for like clean soil, and if we'll have higher levels of dose rate on these detectors, this soil is contaminated. We will treat like contaminated materials, like radioactive waste. Следующий, пожалуйста. Next block is soil washing methods. It's a very interesting method, the contamination methods, because when we developed these methods, one of the variations of these methods was developed in our institution for the contamination of contaminated soils in Kurchatov Research Institution. And we established that main parts of activity includes in the more than 90% of activity is in the small fine particles. Следующий слайд, пожалуйста. Like here, you see main parts of activity is combined with small sized of fraction of materials. So idea is subdivision of big particles on the big size fractions and small fractions for different streams. How it's possible to reach, how it's possible to create. Next slide, please. Hydroseparation. It's a treatment of soil in the hydroseparation methods. When we destroy the soil for small fractions, then separate it in the water media, filter it, and remove small particles. And then only sediments after separation of in the water media of big fractions and small fractions, we will collect small fractions in the with special polymers like flocculants, and we will remove the small fractions and then filter it and dewatering, and then remove to like secondary waste. Next, please. In this case, this is very easy methods. This installation was operated more than 7 years, treated more than 10,000 cubic meters of contaminated soil, and produced clean debris, big size you see, it's a very big size of debris, clean soil with big fraction, more than 6 microns, and small items, very fine parts of particles with a size of less than 5 microns, and the amount of this particle of this parts is less than 20% from the initial part of volume of activity of more contaminated materials, but activity is more than 90% of activity combined in these parts. The contaminated soils with fraction of 6 on 6, up to and more microns is a clean materials, and was used for refilling of storage of old storage of radioactive wastes. Следующий, пожалуйста. This is different view of this technology. So this idea is the same. Следующий, пожалуйста. This is external view of these facilities. Main part of this facility is tank for separation, for sedimentation of fine particles with polymers. And this is segregation of big particles. It comes to these parts of this big debris, big parts of clean soil here, and contaminated materials comes from the dewatering and filtering comes to these parts. The contamination factors is 5, and so after treatment, this facility operates more than 7 years. Следующий, пожалуйста. И следующий. Now, second generation of this facility operated in our institution. The main difference between this, the first installation was practically this factory. It's not transportable materials, but the second generation, we constructed like module, combination of different modules of equipment. And this installation really can transport it from the one site to the other site after a long period of operation. And now it's operated successfully in our institution up to now. Следующий, пожалуйста. Next, subdivision of chemical methods of decontamination or chemical and washing process. It's a application of chemicals for decontamination. Normally, it's possible to decontaminate all volume of volume of soil, contaminated soils, for extraction of radionuclides with chemical agents. Normally, it's phosphoric or sulfuric acids, but in this case, we will apply too much amount of acids. And if you will apply acids for soils, you will not use the soil against for refilling of old sites, because in this case, soils will not be soils, but will be industrial waste after treatment with chemicals, strong chemicals. But if you will apply these methods of the leaching of radionuclides from soil just only for small parts of secondary waste from the soil washing process with hydro separation. We will can maximum removal of radionuclides from volume of secondary waste. So these methods also can be applied. Следующий. Chemical extraction. This is a principle of the chemical extraction. It's discussed. So we will need to place these materials, remove this soil from the surface, from the site, place the tool from the equipment to equipment, to tanks or reagents, and then it will be clean materials like industrial waste or secondary waste like chemical sediments of contaminated radioactive materials, radioactive waste. Следующий, пожалуйста. In situ methods, just only for experimentals, not applied widely. Electrokinetic decontamination. You can apply electrokinetic decontamination with application of electrodes, anode and cathodes into the soils, and after a long period of fixation of these methods, nuclides can be transferred to cathodes or anodes, and you just collect it to this area. But its methods have not a big application, just only for experiments. Следующий слайд, пожалуйста. And phytoextraction. Phytoextraction. Now it's very popular for researchers, these methods. Many researchers happens now in Japan after Fukushima accident. Main idea, it's the plant can remove the soluble radionuclides from the surface. Сейчас заканчиваю. Нет. Plants can collect radionuclides by roots inside the soil, and then transfer its seeds to the plant vegetation. And in this way, we can remove plants, and plants accumulate radionuclides, and then we can remove these plants or grasses and treat it like secondary radioactive materials. It's a very good like idea, but следующий слайд, пожалуйста. But this process is very slow, and each season we can just only small parts of removal of radionuclides from soil. And in this case, we will have a problem with... Следующий слайд, пожалуйста. So, this table is very good for understanding of this process. If we will need to remove, for example, for the contamination factor for 5, like we will reach in our hydro separation facility, activity remaining soil, you see, is we need to very long period of treated of this surface. For example, for removal of this amount of this activity, we will spend a few tens years for removal of this kind of type of activity. So it's very slow process, but it's possible for decontamination also. Следующий слайд, пожалуйста. This process was tested initially in Belarus in the middle of 19th. And also it was for the contamination of strontium 90. And for annual, it was removed just only up to 3% of strontium from the surface. So it's very slow process for decontamination. Следующий слайд, пожалуйста. Bioremediation. These methods also applicable for decontamination of soils, but normally it's used, mostly it's used for decontamination of soils against oil contaminations, because microbes can destroy many chemicals, mainly oil. But also now developed a few kinds of microbes can transfer uranium, for example, from insoluble form to soluble form of uranium. So we can apply microbes to the uranium contaminations, for example, for remediation of enrichment facilities, for uranium enrichment facilities, and we can remove this. We can remove uranium from in insoluble form to soluble form, and then transfer it to some things for treatment of the facility, for example, soil washing methods. И следующий, по-моему, все. Yes, that's all. Thank you for your attention. Practically in time, I think. Any questions?
I wanted to find out what branch of Rosatom is this? We have TVEL, we have Radon, and this one is, what are the acronyms or abbreviations?
12?
This one, VNIM.
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 All high technological research institution of inorganic material. It's very old. Now in this year we will celebrate 18th century of creation of our institution. And initially it was founded for development of materials for nuclear applications. And first, for example, first plutonium was developed, and the first technology for removal of plutonium, first plutonium was accumulated in our institution. It's a very old institution. Now it's operated mainly for fuel company TVEL, for development of new materials for reactor purposes, for fuel rods, for example. And now, and our department is responsible for development of decontamination techniques for decommissioning purposes. And the other department also responsible for development of new techniques for radioactive waste management. So it's a very big institution, a very old institution located in Moscow.
Please add that today, one of the channels of Rosatom announced that today is the birth date
Yes,
of nuclear industry in Russia. So
18th anniversary.
Russia, why they sense we all wait this huge event in history.
No questions. Thank you for your attention. Please.
Decontamination of the soil
Yes.
process and the techniques utilized in the field. But I think there is also you describe if the levels of the decontamination minimize. So how much standardization? What is the standard of the normal soil is compared to the decontamination, contaminated? Which range, values are called the fair or clearance level of the soil? Because there is a background dependent dependency. Maybe higher of the background soil, maybe or not.
It depends on your purposes.
You does not define the level of the clearance of the soil. What are the level of the clearance? We can say the safe soil.
It's very interesting question because clearance level depends on your country laws. And in your country, your regulatory regulations administrations should establish this clearance levels. And for our country, it's also we have the different clearance levels. For it depends because when you will organize and we will develop the decontamination project, decommissioning project, we will create a final state of this facility. What will be green site, brown field, or industrial application, and the contamination levels and limits for the contamination and clearance limits will depend on your final state.
I may agree with you. The background levels of the each country or each level may be the difference. I may agree. But I want to know, I have developed some standard for the soil, sediments, mesh, and other materials. Soils, types of the different, which analysis for another soil matrix. So same way, there is a levels defined. These levels are the maybe called safe. I mean, there is some, you are doing a study in decontamination. There is some values generated. Can you define? Can you tell us what is the level we can say the safe for average value, not for the region wise?
Well, for example, for our facility, because we have also contaminated soils and the second generation of our installation operated for the contamination of our soils and our institution. Because our institution was founded in 1945 and many technologies was new and we have contaminated soils inside territory of Moscow territory of our institution. And we decontaminated very strongly up to background of Moscow city.
Yes. I again simplify this question. Every radionuclide have a limitations, allowable limits.
Yes.
Same matter.
Very big difference between strontium and transuranium, for example.
There are too much of the radionuclide available in the soil. So, like some average given about the potassium, cesium, or something, radioisotope, artificial. Naturally, these are available already in soils. So there is a defined values. Same way, if you are working decontamination process, there will be also other radionuclide find out which values are acceptable for radionuclide. These are not demonstrated by you, or these are values are presented, developed by your laboratory.
I'm not sure that I understand fully your question. I'm sorry. But for the it's a problem of choosing of the contamination methods, you understand, yes? You should develop these methods or apply the contamination methods which you can use for your purposes. For example, if you have a very complex composition of radionuclides, you can apply radiometric decontamination method. If you will have sandy soils, like in our institution we had in the Kurchatov institution, and so you can apply it hydro separation method because it's by segregate very good to find particles accumulated all kinds of radionuclides, and so it depends on your needs and your contaminations, and the nature of your contaminations and nature of your soils. Okay. Okay. No question. Thank you. Спасибо. Да. А тут сейчас унес. Меня. Спасибо.